today we're doing the second lecture of generative models, right? So we have, spent a lot of time earlier talking about MLP for general vectors, CNN for grid data, RNN for sequence data, and then transformers in the use of attention and self-attention and language models. As we can see that transformers are probably being more generic than what we introduced at the beginning, right? So it's not just for language models, it's also for the other kind of data. So I just recalled that there's one part of the story that I may not have talked about, because in the transformer part, there are some recent development which I'm supposed to talk about. Yeah, so I think those were the blank ones that were missing. So for some reason I lost those slides. I was also trying to talk about the visual transformers and other kind of other kind of transformers, but I probably will mention it when we are talking about this GAN that only use attention. Okay, so we'll talk about those. So last time we started talking about generative models, right? Why do we want generative models? You are modeling the distribution, the joint distribution, or the conditional distribution y given x, right? So instead of using a discrete model, which is very fast, like a magnet, that can help you find a needle in a haystack, but it's still a very slow task, right? Instead, you could use a generated model, that model P of y given x, that can make the perfect needle for you directly. So that's one of the motivations. As I said, there are two kinds of ways for this kind of unsupervised generative models. If you are interested in the distribution, you can model the distribution explicitly and estimate the parameters, or you directly generate the synthetic samples, so it's like modeling the distribution implicitly. So as I said earlier, VAE and GAN are corresponding to these two types respectively, right? And before we talk about them separately, I said that you sort of want to unite them, right? We are trying to do a generator, right? So we are trying to generate x, which is the data distribution, right? And the good idea is, in general, is that you want to start with a z, and it's not a coincidence that it has the same notation as latent variables z. So this could be a very simple z that is standard Gaussian or learned, but then given the z, you can use a neural network to model this distribution P of x given z, right? So that is, and this neural network can be differentiable, that can be trained, right, using backpropagation. And one difficulty that we haven't, thought of, it seems straightforward. Well, let's just train this generator networks then. But the thing that is missing, if you think about optimization, is we don't have the loss function. In the supervised learning, you have the paired x and y, but now you don't have the paired z and x. You don't have that, right? So how do you do that? We can utilize, the answer lies in the fact that we can utilize discriminant models again, right? And VAE and GAN, I said earlier on, one is implicitly and one is explicitly modeling the distribution, one is implicitly. And other from that, they are both using the discriminant model for training the generator, but the difference lies in that VAE uses this discriminant model for inference, but GAN uses for classification and like adversarial to the generator training. So that's what is a major difference. So this we have seen before. Let's just quickly remind what we have covered last time. The fact that we are trying to do this generator, right? We're trying to train this generator, and we were asking, well, we have learned autoencoders before, right? And why can't we just use autoencoders for the same purpose, right? Apparently, the answer is like Do-Young said last time. These autoencoders can just reconstruct the input data, whether it's image or text or whatever, right? But it cannot help you generate a new sample, right? So the variational autoencoder is basically taking the view that, well, let's think about this Z not as like, not as the fixed, right, variable, but think about it as a random variable whose probability distribution is to be learned, right? So in other words, if you put a probabilistic spin on AE, you get a VAE, variational autoencoder, right? Of course, let's again look at how we can solve this one, right? So this is what we introduced the last time, right? And we said that, well, the idea is simple, right? But how do we solve this or estimate the model parameters is a problem. What was the problem last time? Anyone remember? So the idea is that Z is simple. This is a Gaussian, right? And we can train a decoder network, which is basically P of X given Z. That's a generator network we want to learn, right? Right? And we can represent it using a neural network, right? Is there any difficulty training this model? Well, we can solve the maximum likelihood, right? Right? The theta is P theta X given Z is a decoder. This P theta Z is a prior, right? And then we try to maximize the likelihood. Does anyone remember or recall what was the problem computationally? What is intractable? The integral is intractable, and just like what you said. Okay, so this integral is intractable to compute for every Z, right? And then this intractability propagates from the likelihood to the posterior as well. That is a Z given X, right? So our idea is that, well, not ours, but Kingma and Welling's idea was the following. So in addition to the decoder network, right, which models the distribution of X given Z, we can define an additional encoder network parameterized by phi that approximates the distribution of Z given X, right? And then what we will do is, there's no magic here so far, because we can rewrite, right? We can rewrite these, likelihood using this additional encoder, but it's not going to change the fact that some terms are intractable until we do something, and that's what we introduced at the end, right? So I used to say that, this derivation should be in our PhD qualified exam. I don't understand that we keep testing students on the undergraduate level courses for PhD qualified exam. I don't understand that. I think the lower bound of a PhD qualified exam for instance, probability should be the derivation of elbow, right? That should be a lower bound, right? So let's look at what this problem is solved. Again, nothing has changed so far. Let's just remind ourselves that we have the encoder and the decoder network, right? And they are sampling Z from X and X from Z accordingly, right? This is variational autoencoder. Variational part is in the fact of the Z, right? Okay, so what we will do is, I'm not going to spend too much time on it because we already introduced it last time, is that we will basically first use the base rule and then multiply the constant, and then we can split this term into 3. And again, as I said, so far there's no magic. Some of these terms will still be intractable, right? So remember, this was not tractable, right? And the fact that we rewrote them does not change the fact that it's still not tractable, right? But the good thing is that now, if we look at this last two terms, these are the KL divergence, right? And the last term is still intractable. Let's look at the first term. First term is, the log likelihood of x given z, right? This is expectation. So this we can do because it only depends on what? X given z is encoder or decoder? X given z. X given z is an encoder or decoder? Decoder, right? Input is z, output is x, okay? So if you want to calculate this log likelihood, expectation of the log likelihood, you can do that through sampling. That's relatively easy, right? And the second term is the KL divergence between this decoder distribution, right? This is a decoder network giving this distribution of z given x. We're calculating the KL divergence between this distribution of z given x, estimated by the encoder, and a prior of z. And the prior of z is standard Gaussian, so we can calculate the KL divergence between the standard Gaussian and this, phi or encoder parameterized distribution very easily. It's actually closed form, right? So, but of course, as I said, you won't expect that everything is now tractable, right? Because there's no magic so far. So you shouldn't be surprised that, the last term is still intractable. So the magic happens when we say that, well, this divergence, yes, it's intractable, but its lower bound is 0. We know that KL divergence is always non-negative. So instead of maximizing an intractable objective function, which is a log likelihood, we can maximize its lower bound, which is tractable, right? Right? Because the last term is just non-negative. So this is called the elbow, right? So this is the elbow, and this is the variational. This is where this name variational autoencoder comes from. So we can try to maximize this one instead, okay? While choosing the proper theta and the phi, decoder encoder parameters. Okay, so that's where we ended last time. Okay, now let's put things together, right? So we are now maximizing this lower bound of the log likelihood, right? We're trying to maximize theta phi. We're given x alone. So the data we are having are just xi, okay? And the parameters are theta and phi. So let's see. We have input data as x, and then we go through an encoder network, and the model is the mean and the covariance, and then this z will be sampled from the encoder modeled distribution, which is assuming Gaussian, right? And then starting from z, we can feed through the decoder network, right? And through this decoder estimated mean and covariance, we can draw a sample from x hat. And then we already knew that the loss is just the difference between x and x hat, okay? Okay, so this, now that we have, if we have trained the autoencoders, once we have trained the autoencoders, we can take the decoder part. After it's trained, we can take the decoder out part and feed the z with just samples from standard Gaussian, right? And then once that is done, we can generate samples. That's how we generate data, okay? So let's summarize variational autoencoders, right? This is, autoencoders plus probabilistic spin, meaning that Z is a random variable, so you have to model those distributions. And the fact that we're optimizing this encoder and decoder is through maximizing the elbow or the lower bound, tells us why it's called a variational autoencoder. Okay, so this intractable density can be estimated can be optimized by its lower bound, okay, the variational lower bound. So the pros and the cons, so you can see that this is a very principled approach to generate models, right? We have this, encoder, decoder, and we have these Gaussian distributions whose parameters are to estimate it. And we allow this Q of Z given X, which can be useful as feature representation, right? I said your encoder, your decoder can be used after trained. Decoder can be used for sampling, and the encoder can be used for feature generation, right? What's the con? Well, we know that we are still maximizing the lower bound, right? So it's an okay choice, but in image we know that it's not really having as good quality as other kind of approaches, right? And the observation in computer vision is that it tends to generate like blurrier and lower quality images compared to the state of the art. We know what they are. They are GANs, right? But still, I mean, they don't focus on the sample. Because GAN really focus on generating the samples, and they don't explicitly model the distribution where VAE does. There are still cases where you prefer using VAE to GAN, right? And these two also can be integrated together as well, right? Okay, so what people have been working on since, including this more flexible approximations, which makes a lot of sense, and then introducing the structure in the latent variables, right? So there's this, GAN regularized VAE that is basically trying to enforce some structure in the latent variables. It's not just like standard zero mean, Gaussian after, or it's not like a generic mean and covariance, but it has some structures. It's like low rank structures or sparsity structures that you can enforce, which is like a prior you put on Z, right? So these are all things that you can do. Okay, any questions before I wrap up VAE? Okay, so this is still very useful. It's not like I keep saying that we don't really just chase the latest. Please don't think that GAN is better than VAE, right? It really depends on what you want. And also, it's not one or the other. Okay, maybe both, maybe neither. Okay, now let's talk about the second type, which is GAN, right? So, as I said previously, there are two ways, right? For this kind of unsupervised distribution estimation. You can estimate this distribution, directly by assuming this, for instance, Gaussian after encoder, right? And estimate the parameters by theta or phi. Or you can directly generate samples if the samples are more important to you, okay? So in other words, if you think about your gap starting from VAE was the quality of the samples, like the blurred or low quality images, then maybe you can give up something and gain better quality, right? Maybe you can give up this explicit distribution. So again, let's remind ourselves, right? As I said earlier, right? Both VAE and GAN utilize a discriminator for training the generator, but the difference lies in how they utilize the discriminator, right? In the case of GAN, they are using this discriminator for classification, which directly impact the loss function. So let's talk about that. Okay, so the GAN, generative adversarial networks, right? So we know that since 2014 we have entered the deepfake era, thanks to this 2014 paper. The problem is that we want to sample from a very complex, high-dimensional training distribution, and there's no direct way to do that, right? So even for the case of this VAE, right, you're already assuming so much, but still you face this intractability issue. So what is the solution, right? This is very similar. This is, again, this is nothing new. This is the same thing I said earlier. Sample from a simple distribution like Z, and then learn how to transform to the training distribution. So how do you go from Z to X, basically? But the difference is, in the case of the VAE, right? In the case of the VAE, you are using a decoder, right? And you have to learn the distribution explicitly for training the encoder-decoder, right? But in the case of the GAN, the trick is different. Let's look at what is the difference, okay? So far, nothing different from VAE, what I said earlier. You use a Z, and then there's a generator network, right? In the VAE, it's called a decoder, right? And you generate the samples, okay? Okay, so the trick lies in this. So it's using the discriminator as a player and playing a game against the generator. So the generator tries to fool the discriminator by generating the real-looking images, and the discriminator tries to distinguish between real and fake images, okay? So that's where the loss is coming from. That's how you train, right? So it's like you have the spear and you have the shield, and you have to, polish both sides, and so that both sides get better and better, right? Right? Without a better shield or without better enemies, you may stop the revolution of the spear or, upgrading yourself, right? Okay, so this is the general idea, right? We still, random noise and then generator network give us the images, and then it's compared to the current discriminator network, and then it tells whether it's real or fake. So you see that the loss is now nothing to do with the difference between the distribution or the maximum likelihood of the distribution. It's based on the images directly, whether it's faked or real, right? If you can fool the best discriminator, then in practice, that's a good generator. So that's the idea. So now let's make it more concrete, right? We still need to talk about the loss function, right? Make it more concrete. This is one of the most important element of an optimization formulation, okay? So as I said, this is a minimax game, right? So, so the discriminator output is likelihood between 0 and 1 of real image. So you give an image to the discriminator, it gives you a probability between 0 and 1, right? 1 means that it thinks it's a real image. 0 it thinks it's not, right? Okay, so the objective function is like the following, right? I give you the answer from in the end, right? So the derivation is non-trivial, but the conclusion is that we're having this minimax objective function, right? So it's maxed over the inner optimization is maximization. It's maximization over the discriminator's parameters, theta d, right? And then the outer is a minimization, right, over the generator's parameter, theta g, right? So within it, let's see that we have the expectation of the log likelihood, which is, this is for the discriminator, right? Then we also have, and here notice that this x is following the distribution of the data. And then we have another, expectation of the log. In this case, we are looking at the expectation over z, okay, the z, and that is following a distribution, and depending on what you do, right, it may or may not be parameterized. And then we are looking at the log of 1 minus the discriminator output for the generated fake data, right? So this is 1 minus the probability is like the probability that is not real, right? And then we are looking at this loss function, So intuitively, this discriminator theta d is trying to maximize the objective so that your data distribution, so that the d of x, right, the discriminator output is close to 1 for x when x is real. And it also wants the d of gz, which is a model generated or generator's output, g of z, right? Because the generator's input is z, output is g of z, aka fake image. So the discriminator wants to make sure that d of x is following the distribution of the data, it's real, is close to 1. And the d of g of z, which is fake image, should be close to 0. That's what the discriminator wants to do, okay? What the generator wants to do is try to fool this, right? So it's trying to make sure that d of g of z is close to 1, so that the discriminator cannot tell, right, g of z is. I think it really, if you go back to our first lecture about AI, I think it makes so much sense about, if you think about it, it's like a Turing test to me, right? But instead of in this case, you have like a real person taking the test. That's the sampled data, and you have a model who's taking the test, but that is like the generator. But then the judge is a model that's to be trained as well. That's called a discriminator. So that's really interesting. Okay, so how do you train this GAN for this minimax? By the way, the derivation of the objective function is very beautiful, actually. But due to the scope of this course, we cannot talk about it. I would strongly recommend you to look into those. But if that is defined, how do we train this GAN? Remember last time, Do Yang was reviewing protein GAN, and he was saying that the ratio between training the discriminator and generator was 1 versus 1. I was quite intrigued. But we know that the fact is you have to train this discriminator and the generator alternatively. And you may train n steps for the discriminator and the m steps for generator, and there's some ratio between n and m, right? The thing is that if you don't train them properly, you could have very dumb discriminator and a dumb generator at the end, right? All right. So usually, does anyone remember? Usually, you have to train discriminators more steps or generator more steps. Do you have to train which one would you spend more steps training? The generator? Anyone else remember? You train multiple steps of the discriminator and then train one step for the generator? That's what I recalled as well, but let's confirm that after the lecture, right? But in the case of protein GAN, they tuned the different ratios and found out that 1 versus 1 was the best. I don't know for what reason, but let's remind ourselves that in the early days, GAN was on computing faking images, so their generators and discriminators are usually CNN, right? But in the case of protein GAN, we know that the generators and discriminators are using self-attentions or transformers. Whether that causes any difference or not, we don't know exactly. Okay. And how do we do that? So you can first do the gradient ascent because you are maximizing on the discriminator, right? So you are maximizing this inner function, and then taking the last step's optimal solution as the optimum. Then once that is done, right? Then you just have to minimize over theta g. But in the step of theta g, the first term of this loss function, right, is not dependent on theta g, right? So that's why in the first step, once theta d is trained, is optimized, we fix that value and then try to optimize theta g. So the first term actually doesn't change when you don't change theta d, right? Only the second term, right, is changing when you change theta g. So when you optimize theta g, you can just do the gradient descent on the second term alone, okay? But in the first step, when you updating the discriminator, it actually enters both terms, apparently, right? There is theta d in both cases, right? But theta g only appears in the second term. So that explains why these two objective functions are slightly different, okay? Because in the minimization's eyes, this first term, once it's optimized, is a constant with regard to theta g. Okay, so of course, training GAN is always an issue, right? So training GAN is an issue, right? So let's look at, for instance, this is D of G, which is like the probability of the faked image or the model generated images, right? And then the y-axis is like the loss function, right? So basically what it's trying to say is that when initially the sample is apparently low quality and very likely fake, this kind of slope is kind of flat. It's like when you needed to optimize or boost your generator the most, this gradient can be giving you very flat information, right? And then when you are really getting to be having really good images, like the probability is above 0.8, this landscape gets steeper, and so that's some like a dilemma. It's like when you wanted to boost the performance the most, that's where you start. You don't get much help, right? It's like the rich getting richer at the end. So how do you help this training process, right? So what you can do is sort of changing this landscape. So instead of minimizing the likelihood of the discriminator being correct, and now you can maximize the likelihood of the discriminator being wrong, which is the same, right? But which is the same for your training purposes, but the landscape is very different. You see, right? So this is when you use the blue was what we see before, minus log d, right? Minus log d g, right? But if you use log 1 minus dg, that's log 1 minus dg is this one, right? And then green is minus log dg, which is this one. So at the beginning, it's much better if you can train this likelihood that this discriminator is wrong, okay? So, or minus log d, okay? So, or minimize minus log d, minimize the negative of the probability likelihood. Apparently here you have much better gradient information, right? So that's becoming a standard practice, right? But in general, jointly training these two networks can be unstable, and what we are trying to do is changing the landscape of the objective function without changing the resulting optimal solution, right? So this is actually a more general topic than what's just being addressed here, okay? So that's another thing we like to do from the perspective of optimization in the deep learning. Okay, so now let's see the pseudo code, right? So for a number of training iterations we do, right? For k steps, we do sample the mini batch from the noise, which is like a z. This is a prior, which could be a standard Gaussian, right? And then you also sample the same amount of true data x, right? And then you you try to solve the you try to maximize what is written here first by adjusting the discriminator's parameters, okay? And then you do that k steps, and then this is the discriminator, and then after it's finished, you try to optimize the generator parameters by using what was described before, basically only the second term, right? And notice what is written here. So instead of minimizing the second term, I'm maximizing log of this d without 1 minus. This is what's written here, right? That's exactly the trick I was talking about earlier, right? So minimizing this minus log, which is green, minus log d, okay? So that's what is actually being done. And apparently we do k steps of discriminator and 1 step of generator. So sometimes people find k equal to 1 is more stable. Sometimes people find k bigger than 1. But usually, we try to train the discriminator first and multiple steps before updating the generator for 1 step. Okay. So that was the answer to my earlier question. So once the model is trained, just like the VAE, once it's trained, you can take the generator, right? You can take the generator to sample, right? So you can give Z, you can sample Z from random noise, standard Gaussian, and then in the end you will get these images, right? And let's look at a few examples, right? So, this is based on generating generating 10 numbers, and this is for like generating images, right? So, they were trying to see how the generated samples compare to the nearest training example, right? So I think that nearest neighbor is probably defining the latent space, right? And then they go back to the original X space and then see what it looks like, right? So it sort of explains how this generation process is done. And back then I said the generator and the discriminator for computer vision is using CNNs, right, convolutions. And I don't want to talk too much about it, but back then the generator is, upsampling because it's going from Z, right, to X. It's upsampling network with fractionally strided convolutions. Because we said when we describe convolutions, do you remember that stride is to change the resolution, isn't it? So back then, we say that our strides are all integers, so the resolution always gets smaller. But you could actually use fractionally strided convolutions as well for upsampling. So that's what they use for the generator, right? And the discriminator is a standard convolutional network because it goes from high dimensional X to Z, okay? And there are some small changes that, non-trivial changes, if you wonder, what else do you need to do when you introduce these convolutional neural networks to GAN, right? Something is, for the generator I already said, let's use the fractional strided convolutions. And the discriminator, you just use the strided convolutions because it's downsampling. Both need to use batch normalization and remove fully connected hidden layers so that you can have deeper architectures. Use ReLU activation in the generator except for the input, which use hyperbolic tangent. And then in the discriminator, use leaky ReLU. Some of them were, just empirical, but sometimes when you think that, the general idea works, there still needs a lot of things to tweak. So in that case, you really have to determine what are the major issues and what are the minor issues. Actually, in research, just like in life, what is difficult is, but very necessary, is knowing when to persist, when to take a detour, and when to give up, right? That's the most difficult thing, right? So that means you need to first determine the priority. So if this is a major thing, like I'm trying to make this two-body game work, and GAN is my major idea, then I should focus on that. But there are these tiny things that could be a make or break. So you have to determine whether this one has a high priority or not for your bigger picture, and then you have to decide, when to keep going and when to stop or when to take a detour. And that's never going to be an easy question, right? But that's life. And this is a generator I was saying earlier, right? It's upsampling, right? Starting from 100 dimensional Z to a 64 by 64 image. And these are some of the images that they generated. This was iClear 2016, 2 years after the NeurIPS 2014 paper, right? So, one thing you can think about is, of course you can say this image look like bedroom, look amazing, like real. Another thing is that you can sort of do the interpolation. Imagine that you have two images, right? After the GAN is trained or VAE is trained, it's a latent variable, right? Now, if you have two latent variables corresponding to two real images, you wonder, what if I make a line between the two and sample between? In other words, what if we interpolate the two real images, and what do we see, right? So this is basically what they are trying to see, it's like interpolating, but it's like controlling, right? Going from, for instance, one image to another, right? Going from one image to another, you see like a series of intermediate changes, and it's like I think in computer graphics or in movies, you see these special effects that, especially in those superheroes, some of them can change their shapes, right? They can change into something different. Imagine that this is the shape before and this is the shape after. And previously, the technology may be giving you less smooth interpolation, but now this can be done in a much smoother way, right? So imagine that. And another thing is, the interpretability, or something I really like, is the following, right? So you could start from, you could sort of extract the latent representation of something abstract and do the transformation to some images. So imagine that, you have a lot of images of smiling woman, and then you have images of women with neutral face expressions, right? And then you have images of the neutral men, right? So what you could do is the following, right? So if you train your models, and then you can get the latent representation of the smiling woman versus the neutral woman, and you take the difference between the two, and that is like a vector for smile, right? And then if you put that vector on top of the latent vector of neutral men, and then decode or generate back to the image, what you get is smiling man, right? So this is something that is very interesting. But I want to remind you that smile is already a disentangled factor compared to the facial expression, right? What's here? You have, the eyes, nose, and mouth, and so on. And on top of that, there's a smile, right? But if you talk about proteins, right? If you talk about proteins, how do you disentangle those factors? That's something to be, worked out, right? But this is a nice demonstration. I always think about this demonstration. This is the same. You have the pictures with glasses and no glasses. You more or less make the images, you don't have the paired image. You never have the paired image. You never have the same person without or with images, okay? You have just the distribution of men with glasses and distribution of men with no glasses. You make sure that these images are more or less normalized so that their major differences lies in glasses, okay? And then you do the same, and then you get this woman with glasses. Of course, this was apparently before 2017, 18. You see that the quality isn't great, but now it's much better, right? So there's the so-called the GAN zoo. There's WGAN. We use the Wasserstein GAN in the loss that address the mode collapse oscillation. It basically replaces the loss, which is actually a Jensen-Shannon divergence, which we didn't dive into, with the Wasserstein distance. Okay. And then there's conditional GAN when you have additional input Y, right, in addition to Z, and then you can generate samples conditioned on the label Y. There is an info GAN, training the conditional GAN, but in an unsupervised manner. Bidirectional GAN, BiGAN, and then cycle GAN, which is image to image. Then there's a bicycle GAN as well. Then there is a super resolution and the flow-based methods. So a lot of this, this was just summarized a couple of years ago. There's way more things going on since then. And let's summarize again. What about the GAN, right? So it doesn't really work with explicit density distribution. It just tried to optimize the samples, and then the quality of the samples or the loss on the samples, on the generated samples, is just to make sure that they cannot be discriminated by the best expert. But the best expert is also, the discriminator expert, is also trained concurrently with the generator. So it's a two-player game, right? So it's learned to generate from training the distributions through the two-player game. So the pros is that, they focus on the sample. So the samples can be really, great, right? They look real. The cons is that, it's a trickier to train. And it cannot do inference, just like VAE. For instance, we want P of X or P of Z given X, that VAE actually already modeled those, right? And we already introduced this latest developments. Some are trying to have better loss, right? Especially Wasserstein GAN. Some are trying to condition GAN for all kinds of applications, right?